Okay, students, let's finish the topic about indirect adaptive control. We have finished the adaptive control with pole placement. Now let's talk about indirect adaptive control. This is very easy, actually. Today's lecture on this will actually be short. The overall scheme, let's use the same RST structure, and the plant is the same as before. We're still doing pole placement, so there's still some pole placement equation for characteristic polynomial. So pole placement is designing essentially the closed loop from here to here, where the characteristic polynomial is so this is same as before. And then the numerator is going to be q negative db q. Same closed loop transfer function, and the pole placement is designing this part. The condition, let's talk about the condition. If B is cancelable, then we can use direct pole placement, direct adaptive control. Now, the condition is assumption is B is not cancelable. It contains some unstable zeros inside. So we cannot let T to be the same as before to contain, to cancel. So let's do T. Previously, T is D prime. Well, D prime is the selected, is part of this pole placement, contains partially all the poles inside here. And then S, we cannot assign to be BQ inverse times S prime. All right? So we cannot assign this. So it cannot have a common denominator of B in here that will cancel with this. So the same assumption is, and then A, we don't know the plant. The plant is unknown. Unknown parameters. So under this type of setup, the indirect adaptive control does this. All right, so indirect is in the sense where we design the pole placement to be this. So we have the entire polynomial for the denominator. This is design. All right, so this will, and then design T this way. T to be DQ inverse, and then some part of B inside. So let's do it this way. Or this way. So I'm going to explain these a little bit. So T is designed to be to cover the entire closed-loop polynomial. All right, so here, from here to here, this is GR to Y. So the point is, I'm going to design this feed-forward controller to cancel the entire denominator. This is possible because all the roots here are stable. So I can do stable pole zero cancellation. And then I'm left with something remaining over here, right? This is going to lead us to the block diagram with R star K going through D, E, and then this part, the closed loop transfer function with Q negative D and B in the numerator. Okay, so I'm canceling this. I cannot cancel B because it has unstable zeros inside. So this is a compromise. We no longer get perfect tracking result as we could have done. Instead, we got this. All right, so this gives us the design equation. After the pole zero cancellation, we have this is RK. If B is B0, B1, Bm, then B1 is basically the DC gain of this filter. So replace all the Q negative 1 with 1. So you get B0, B1, Bm. All right? So the purpose to do this is to assure, so this is YK. The purpose of doing this is to assure the DC gain from R star to Y is going to be 1. All right, so this whole DC gain is basically replace Q inverse to be 1. Then you have the DC gain is D1. This is going to cancel with this, so actually it wouldn't matter. All right, so you at least have unity DC gain. All right, so at the steady state, you still have good, reasonable tracking. So this is for this design. And this is perfectly feasible, all right? This is a constant. This is just a number, so it doesn't have unstable poles. And all these are stable zeros in here. And then cancel out. So the design, if we write it in a slightly different language as we have done before, is RK. So let's focus on RK signal. RK, on the left-hand side, it equals dq inverse B1 R star K. And then from the right-hand side, we have YK is Q negative D BQ inverse DQ and RK. So RK is therefore DQ this DQ inverse YK equal to equal to BQ inverse RK. I'm going to put Q positive D here. So I'm creating the term that's familiar to us in direct adaptive control. So massage this equation to here, we get BQ inverse YK plus D equal to BQ inverse RK. All right, so on this left-hand side, we can have something similar. So this is going to actually give us the design equation. So we're going to design my overall reference signal R star K, similar as before, as YD K plus D. Then we will have DQ YD K plus D equal to B1 RK. All right, so this way, combining these two, we can have the tracking result D Q Y K plus D, all right, is going to equal to BQ inverse RK, and it equals to BQ inverse RK is DQ inverse Y DK plus D over B1. All right, so from here we can get RK and then put it in here to obtain this boxed equation. So we see YK, so the purpose is we see that this is not really perfect tracking, but still in some good sense, we can have DQ inverse YK plus D minus, we can write it in a similar form as before. All right, so factor out the DQ inverse term, then we can have YK plus D minus this BQ inverse B1 times YD K plus D equal to 0. This is the achievable design when you have unstable zeros in the plant. All right? So not perfect compared to cancelable zeros, but still you have, at least at the steady state, DC gain, you're going to be able to track accurately. This is not the best thing that we'll be able to design. This design improves upon this a little bit. All right, this is going to give something known as zero error, zero phase error in the design. So to illustrate this, let's work on this a little bit more. So my notations are, so you can see this is the same as before, DQ inverse. And then this BQ is denoted as replace every Q inverse with Q in this polynomial. All right? And then this is going to give us draw this similar picture, R star K. This time I'm going to specify R star K equal to Y dk plus D directly. And then go through dq inverse bq b1 square and rk yk. It still does the DC gain type of trick. Okay, you still see this B1 here. It's going to create the same DC gain as this BQ inverse term. Let's take a look at this extra term here and take a look at this square term and understand why they happen this way. So the overall DC gain from the left to the right is going to be D1, B1. All right, Q is, if Q inverse is 1, then Q is also 1. All right, so DC gain is essentially replace Q inverse with just 1. Then this is the first part, and B1 square times 1 times B1, and then D1. So under this design, we also have unity DC gain. All right. The only difference is the overall transfer function now is going to become overall dynamics. It's going to become Q negative D BQ inverse BQ over B1 square after this cancellation of the stable poles and zeros in here. This one compared with this one here, it has the nice property that this always have zero phase. If we don't, I'll explain it a little bit more in here. So continuing from there, we have Y dk plus D on the left, and then Q negative D BQ inverse BQ B1 square. Then this is YK. Or in other words, we can write it as Y dk for analysis goes through BQ inverse BQ all right. So the name zero phase arrow comes from the fact that if we consider this delay term separately into the reference side, this transfer function, it always have zero phase. Okay, so here you can see that as example, BQ, let's say this is 1 plus 0.5 Q inverse, and then BQ is 1 plus 0.5 Q, and then this is 1 plus 0.5 Q inverse. The frequency response of these two, they are always complex conjugate of each other. So the frequency response which is obtained by evaluating this polynomial at Q equal to EJ omega. then the frequency response of the top one is always, because of this inverse and Q inverse and Q term, they are always complex conjugate of each other. So by this design choice, you can see this equals B E negative J omega complex conjugate. All right, so BQ you can see the result is that if you do multiply things out, you're going to get 1 plus 0.5 Q plus 0.5 Q inverse plus 0.5 square is 0.25. All right, so it has this symmetric kind of coefficient. And it always have zero phase. If you plot the frequency response, then the frequency response of this whole thing is going to look like magnitude and phase. Always zero phase. And then the magnitude looks like usually something like this. This is a low-pass filter, you see. It passes through low-frequency components, not high-frequency components. This type of filter is ideal for control purposes, for tracking control purposes. You don't have phase error. So let's say YD is a constant. Let's say I want to track a constant 2. Then let's take a look at YK, what it equals to. YK is going to equal to BQ inverse BQ over B1 square. And B1 is 1 plus 0.5, so it's 1.5 square. And then BQ inverse times BQ is going to give us, and this is YDK. Is going to give us here 1.25 YDK plus 0.5 YD. This is one step advance, K plus 1, and plus 0.5, one step delay. If the desired reference is a constant 2 here, you can see the result is going to be, these are all the same, so it's 2, 2, 2. The result is going to become 2 times 1.25 plus 1. So 1.5 squared is 2.25. Then this is 2 times 2.25. It equals 2. It equals the reference. All right? So you get perfect tracking if it's a constant reference. And it can be reflected over here as well. A constant reference is somewhere here. It doesn't have any frequency components, all right? High frequency means you have changing signal amplitude. So you got perfect tracking here. Similarly, as another example, if you have, say, a ramp signal, alpha times k, let's make it simple. Let's do 2k. This signal is, all right, going up with respect to time. Then you can similarly do the same thing and obtain your output. It's going to become, so this doesn't change, and then this signal is still valid. We replace YD with this, so you're going to get 1 over 2.25, 1.25 times 2k plus 0.5 times 2k plus 1, and then 0.5 times 2k minus 1. Then you're going to get 1.25 times 2k plus this negative 1 and positive 1 cancel out. You're going to get plus 1 times 2k. And then the result is 2k times 2.25. So for a ramp signal, you also get perfect tracking with this type of design, which is not true if you just use this. You can check. If you just use this type of design, you won't be able to get perfect tracking with this type of signals. Because the true reason is because this is not a zero phase type of structure in the end. So that's two designs, essentially, to give you still some good tracking performance. All right? This is if you really solve for SR, all right? You know A and B, you can solve for SR, so you will know, you will be able to implement T, S, R, everything, right? If you know B, then you can design T this way. The adaptive portion is going to do one simple change and make it work. So the adaptive version is identify A first. Do this direction. So identify A with some adaptive portion, and then B with some adaptation algorithms. And then solve for, at each step, after you identify this, then solve for S and R. From the Diophantine equation. You still design D. All right? So that doesn't change. What is changed is how you obtain S and R. And then implement T with either version of this. Right? Either version of this requires some knowledge of B. That's why we still need to do adaptive control. All right? That's the general picture. Now, in practice, just to be a little careful, so caution, it's about the orders of the controller that you need to select. All right? So whenever you see Dauphin-Tai equation, be a little bit careful about the orders of the equation. The orders are A, let's say, in this adaptive version of the Dauphin-Tai equation, the orders should be as follows. A is n's order, and then B is m's order, so this is D plus m's order. So you should select your controller to have a unique solution. S hat should be D plus m minus 1, and then R is n minus 1. And your desired closed-loop polynomial should be n plus m plus D minus 1 at most. Okay? This is the condition for the Dauphin-Tai equation to be solvable. So after you do all these, then you implement your control law, adaptive control law. UK is here. This is the same as structure as before. Minus R hat and then YK. All right? So feed forward pass, feedback pass, and then 1 over S hat. So this is the recipe for indirect adaptive pole placement. This is if we still stick to this RST type of structure. Now, the concept is pretty generalizable. Let's say in practice you are using some other type of control structure and you don't know the Planck models, then you can do something similar to this recipe. So let's say we don't have this RST structure anymore, and we just want to design some controller if this Planck parameter is not known, right? So we can still do pole placement type of design. So assumptions are, or the Planck parameters can change. Then we can still do update, let's say, do some type of PAA to identify plant. And then if we want to do pole placement, then we can we can still use the identified Planck models to solve for R and S. And then implement the control structure in here. All right, so this is for pole placement. There can be other type of algorithms for designing R and S, but scheme is pretty general for any type of indirect adaptive controls. So that's the indirect adaptive control algorithm and then how it can be generalized to broader control structures beyond pole placement. That will be it for today.